Hi, everyone. My name is Brad Topol. I'm an IBM Distinguished Engineer, and I'm also IBM's Director of Open Technologies. And I've been contributing to open source over the past 10 years. I've been a Kubernetes contributor, an Open Telemetry contributor. I'm a SIGDocs maintainer and former workgroup chair for the SIGDocs localization team. And I am here to talk to you about an introduction to cloud-native technologies. And we're going to attempt to do a whirlwind tour and cover a lot of stuff, kind of give you a taste of a couple different projects. So we're going to see how this goes. The first time I've given a talk like this and tried to cover this much material. So if we're going to start talking about cloud-native, we got to go back and first start talking about containers. So I want to take you back to 2012. Folks like myself were working in cloud platforms, but what the cloud platforms like OpenStack were focused on were what were called virtual machines. And so the virtual machines were a pretty good improvement over actually trying to run something on native hardware. So with a virtual machine, you could get your web application server up and running, you could get your database up and running, and network configured pretty quickly, much quicker than what people were doing before, which is you'd call the person to install the web, the application server, install the database. So things were better, and you could do some snapshotting, and the virtual machines were pretty good. But in 2013, at PyCon, a guy named Solomon Hykes gave a presentation where he said the following. The security in Linux has gotten a lot better, and the process isolation has gotten a lot better. So while you all are doing all this stuff with virtual machines, I can take a process and I can use secure Linux to isolate it, give it its own memory and CPU quota, give it its own little layered file system, and I can then also do snapshotting like virtual machines. And so what he showed was an alternative to virtual machines based on a process being isolated and given its own resources. And for the folks like myself that actually got to try this, it was amazing. Because to start up a virtual machine takes a long time. To snapshot a virtual machine takes a long time. Start up a process takes like milliseconds. And snapshotting the process, it had a layered file system, so it did just the diffs, and that was incredibly fast. And so what Solomon Hykes started and showed at PyCon was really revolutionary, and he said he was going to make it open source, and he was going to call it Docker. Right? So he was going to call it Docker, and that's sort of where the container started. And so what is a container? Again, it's a container is just a Linux process, and it takes advantage of advanced features to provide isolation. And like I mentioned, they get their own file system, their own CPU and memory, and they get all their libraries packaged up with them. So all the code that process needs to run is packaged inside the container with it. So it's very easy to move them from public to private clouds. You can store them as images just like you could virtual machines, and they're much smaller though than virtual machines, right? And so what you're seeing here, and I'll go to the next picture, they're much more efficient than virtual machines. So what happens on a virtual machine? You've got your application, and then you've got your virtualized Linux kernel, and so maybe you can get like, say, 3 of those on a server. And when you're doing system calls, the system calls are going from the virtual machine through the virtualized Linux kernel into the real Linux kernel. There's a lot of overhead there. But compare that to what we can do with container-based applications. Again, it's just an isolated process packaged up with all the libraries it needs. And so it's not going through a virtualized Linux kernel, it's going through the real Linux kernel. So we can pack a whole bunch more of these on a machine. And as I mentioned, so it's more efficient, and developers loved it because you could quickly set up a development environment where it was the tools that you needed, the software package that you needed, and it was all in that container. So very, very popular. So we've got these things called containers, but if you want to think about doing things cloud native, that means being able to at least run them across a cluster, right? So how do we worry about that? And so we needed some software out there that would be able to say, I manage and provision containers. And way back when, there were like 3 choices, believe it or not. There was Kubernetes, which originally started at Google, and then eventually got put into a foundation. There was Docker Swarm, and there was Mesos. And what happened is the Kubernetes had some really key features for managing and provisioning containers. And they started a foundation called the Cloud Native Computing Foundation. And so with the really cool features and having a foundation behind it and a level playing field, all the industry sort of went to Kubernetes. So what is Kubernetes? It's enterprise level container orchestration. It's going to allow you to provision, manage, and scale applications that run as containers across a cluster. It's going to allow you to manage the resources that they need, so the volumes, the networks, the secrets. And the coolest thing about Kubernetes is it's a declarative model, right? So it's a declarative model. I used to make a joke where I'd say, how many of you out there have ever worked directly for a vice president? Anybody here work directly for a vice president? Gentleman here. And so he'll know, when you work for a vice president, basically the vice president comes to you and says, I need this to happen. Brad, go make this happen, right? Doesn't tell you how to do it. He says, I need this to happen, go make it happen. That's how Kubernetes works. It's a declarative model, and we're going to see some examples. But basically with Kubernetes, you get to be the vice president because you say, Kubernetes, I need this to happen. Maybe 4 copies of my application running, maybe 8 copies. Go make it happen. And so that was really the power of Kubernetes, that highly scalable, declarative model that could survive failures and restart stuff when things failed. And that was sort of the key features that we're going to see. So just real quick about the Kubernetes architecture. There's sort of a main node, and there's worker cluster nodes, and you can interact with it through a command line interface or a REST API or a UI. And I can't go into too much detail, but the idea with Kubernetes is it's allowing you to get your containers up and running and get them scheduled on the worker nodes to run. But the smallest unit, as we'll see, is not a container. They introduced a new concept called a pod. Okay, so in a pod, that's the smallest unit that Kubernetes manages and worries about scheduling, and it can have 1 or more containers. So that pod is going to contain the container, the volumes, whatever you need. It's the smallest deployable unit in Kubernetes. And the way to think about it is, well, do I put 2 containers in the same pod, or would I put them in different pods? Well, applications that run in the same pod, they're going to share an IP address and port space. They're going to share a host name. They're going to be able to communicate via native interprocess communication, and they can share mounted storage. And then if you have applications in different pods, they're going to have different IP addresses, different host names, and it might as well be as if they were running on different servers. So when you're designing your pods, typically you ask, well, will the containers work correctly if they run on land on different machines? And if the answer is yes, you typically want to put them in different pods. A classic question I always ask folks is, if you got an application server and a database, would you put them in the same pod, or would you put them in different pods? Anybody want to take a guess? Different pods. All right. So, and one of the reasons you put them in different pods is typically the scaling you need is different. So if web application servers, you scale really high up. Databases, you don't scale as much. And so it wouldn't make sense for them to be in the same pod, because when you scale that pod up, and we're going to show how Kubernetes scales a pod up, you're going to want to scale them at different levels. So just real quick, the features that you get with your Kubernetes pods: you can create them, list them, delete them. You can run commands in those containers that are running in the pods. You can copy files to and from the containers in the pods. Really cool feature about Kubernetes is it's got liveness probes and readiness probes. What it really improved on beyond the previous cloud infrastructures that some of us worked on is it really made it easier to figure out, is stuff really running or not? Because it wanted to be able to know, if things aren't running, let me start up a new version for you. And so if you're the person who is going to get paged out in the middle of the night because the application crashed, which would you rather have? That pager go off and told the application crashed, or The application crashed. Kubernetes recognized it and said, that's not a problem. I'll just start 4 more pods up and save the day. I think we all know which one we want. We don't want that pager going off, right? And then if we look on the right here, we're going to see what's called a YAML file specification. Again, I said Kubernetes uses a declarative model. Declarative model. You declare what you want, and you use these YAML files to do that. And so looking at this example, there's a resource type called a kind, the kind value. And again, the simplest one we have in Kubernetes is a pod. You give it a name. You say what's the container image it needs to run. And then you can say what port it's running on. And so that's that declarative description. And then we just run a command called kubectl create, and we pass in that YAML file. Kubernetes takes that YAML file and goes, oh, Brad wants to run this container image as a pod. Let me go schedule it on one of the worker nodes and make that happen. So very, very powerful. The built-in capabilities of Kubernetes are really, really powerful. So the first one we're going to talk about is what's called a replica set. And again, the replica set allows you to manage multiple copies of your applications that are running as pods, right? So it's automatically going to schedule them, and if something fails, it's keeping track. And if you look, I have it in red here. I'll go through the YAML specification in a second. But here I'm saying I want 3 replicas. Well, if you tell it you want 3 replicas, the replica set, if you've only got 2, what's it going to do? It's going to start another one. And if you got 4, what's it going to do? It's going to scale it down. So the replica set's pretty powerful. It adds a little bit more to the basics specification. And I have a lot of material, so I'm going to go a little faster than I like to cover. But again, this is the kind is a replica set. It uses labels. And so you label the different pods, and that's how it knows which pods it's responsible for. So you get to describe how the labels work, and it's saying, hey, there's an app label with the value guestbook and a tier label with the value front end. The big value here is you say the number of replicas you want, and then you can build a selector and say, hey, this is how we match those pods. And so that's what's happening in that match expression. And then at the bottom, just like the previous declaration, we get to declare that it's managing containers. There's the name of the container, the actual container image, and what port it's going to run on. And again, we can use that kubectl create command with that YAML specification. And Kubernetes is going to take care of the rest. You're now going to have a replica set controller up and running. It's going to be managing whatever number of copies of the replicas you told it. And if you got really bored, you can then update it. You can do a kubectl apply and send in an updated YAML. And so instead of 3, you're going to tell it 6. And now we all know what it's going to do. It's going to go, you want 6? I'm going to give you 6. And it's going to find a way to get 6 up and running. So replica sets are pretty good. They've got some commands like being able to delete replica sets and delete the pods underneath them if you want. It's also got, and we'll talk more about this later, but built into Kubernetes, unlike some of the other previous cloud platforms that said they were going to give us auto-scaling, they promised us auto-scaling, and then the auto-scaling was terrible and we didn't get it. Kubernetes really gives you auto-scaling, and there's a simple example here that says, hey, start at 3 pods, go up to a max of 7, and keep going up when the CPU percentage is getting above 80%. So replica sets are really cool. You're never going to use them. Never going to use them. And the reason you're not going to use them is because they got a better version called deployments. And so that deployment is going to give you everything that a replica set gives you, but the deployment also worries about rolling out new versions of your application. So it's going to enable you to easily move from one version of your code to another version of your code, and it's going to do the health checks and what have you. And so just like a replica set, we get to set the replica value, and we can apply that. So just like a replica set, we can do that. But then we can also do some neat things where we can add an annotation to say, hey, we're making a change. We can update the image. We'll update the image. And then we've got some values for how to do the update. There's a couple different choices, right? So let's say I've got 3 copies of an application. One way to do it is I can do a blue-green deployment. So I have 3 of the current application. I wait till I get 3 of the new version of the application, and then those go away. I could do that by setting my max surge of 3. If it was a 3 application, that's the max surge value, allows me to surge beyond my current number of pods. And the max unavailable says how fast can I destroy things, how many can be unavailable at a certain time. So built into Kubernetes, you've got great support for scaling, you've got great support for rolling out new images. You can roll out just a little bit and see how it's going. You can pause it, you can revert it. A lot of power there to look at. Now, another thing to look at is usually when cloud infrastructure uses what's called a load balancer. But in Kubernetes, you've got these pods running all over the place, and every time a pod crashes, Kubernetes is going to automatically start one up maybe on a different machine. So if it's on a different machine, load balancers aren't really good with that. Short answer is Kubernetes is what's called a service object. And that is a built-in, essentially, load balancer for your pods. You can give it a virtual IP, which is basically called a cluster IP address. And that's something you can put in DNS. And so through that IP address, the service object is going to allow you to load balance across all your pods. It's very, very powerful. Readiness checks are built in. It's only going to send stuff to pods that are ready. And if we look, there's a simple deployment here on the right, get deployment with 3 replicas, and then we create our service object, and it runs on port 80 and connects to the containers in the pods that are running on port 8000. So there's some commands there on how to do that. So very powerful there. Again, auto-scaling built in. Over here on the right is a very simple example. We're going to get an application up and running with 3 replicas. We're going to get a service object. And then we're going to set the auto-scaling in that 3rd command and say start at 1, go all the way up to 10. And then the last command is just a fake load generator. And so if you run those 4 commands, you can actually make Kubernetes auto-scale in pretty 4 simple commands and demonstrate it. So that's a lot of fun. So now we're going to switch topics. All right, so we've covered containers, we've covered Kubernetes. I'm doing OK on time. Here's the neat thing. I talked about containers and I talked about Docker. And so Docker has these things called Docker files that describe how to build the image, right? How you build the image, you take a base image, you put your custom code on it, you do some other fancy stuff, and you build a container image. And that's all declared in a Docker file. Kubernetes allowed you to now declare things with those YAML files, okay? So look at where we're getting to. We're getting to pretty much all the config we want to do is described in either a YAML file or a Docker file. Now, in the old days, we had to do everything with scripting, okay? So in the old days, we had Chef, we had Puppet, and we did all this scripting. And if you wanted to know how the configuration and deployment was going to go, you had to be smart enough to read the scripts. But now there was a fundamental change. I don't have to go read a Chef or Puppet script. I can actually go look at the Docker file and look at the YAMLs. And by looking at that configuration, I can understand how I want things configured, how I want things deployed. And once you've made that switch, now it becomes much easier to talk about what's called continuous integration and continuous delivery, CI/CD. And so we're going to define these terms really quickly. In continuous integration, what happens? Well, you push your little changes into GitHub, right? And what happens is we're going to create a build, and we're going to see if we pass the unit tests. And if we pass the unit tests, then we're going to typically result in creating a new container image and putting it in a registry. That's what people think about when they say continuous integration. And then continuous delivery is an automated release process. What's going to happen there is you kick off the continuous integration stage, and then when everything looks okay, you can manually push a button and you can actually deploy. And so we typically call that continuous delivery. And then continuous deployment is the crazy step where you're like, what the heck? If it passes all the unit tests, just send it right to production. A little dangerous there. So if you were curious, that's CI, CD, and continuous deployment. So let's talk about the fundamentals here. When we try and teach continuous delivery, small batch changes. All your changes should be very incremental and finite. We source control all the things. Those Docker files, those YAML files, they're all going to be in a GitHub repo somewhere, right? So we source control them. And what we're doing here is, containers are really good at, one thing I mentioned earlier is the containers, since you package up all the exact package of libraries you're going to use, that old thing, well, it worked on my laptop and then it didn't work on production. That hopefully mostly goes away, because what happens is when you go from your laptop to production, you're running with all the same versions of the libraries that you packaged in the container, right? So, giving you developer access to production-like environments, and we talk about how to get early on in the process, start worrying about you doing health management, log collection, so we call that shift left on the operational practices. And again, we're doing continuous integration of changes. The changes are built and deployed on an ongoing basis. That is really, lots of automated testing and validation. That is sort of the fundamentals of continuous delivery. So let's talk about the open source tools that are very popular in the cloud native world for doing CI/CD. The first one is called Tekton. It's a CI/CD system, and it runs as a Kubernetes-based application, right? So it's eating its own dog food, right? It's actually running as an application. Basically, it's got the concept of tasks and pipelines. And so, the tasks are these reusable build units. So, I've got a couple down here in the bottom left. One task would be, we maybe clone the content out of the GitHub repository, then we do some test, and then another task might be to build and publish the image, and then maybe another task might be to deploy the image. So you build up all these reusable tasks, and then Tekton gives you the ability to create what are called pipelines. And you can reuse the tasks that you want. You can put them in pipelines. You can say which items can be done concurrently, which ones have to be done sequentially. The sample Tekton pipeline I have here is listed, and just some basic operations. And then on the right, there's a whole bunch of reusable tasks that are available in OpenShift. That's sort of a version of Kubernetes from Red Hat. And so, there's a lot of image building and stuff there. I won't go into too much detail. So that's a great way to do things. Tekton's very popular. A lot of the AI technologies like Kubeflow and other stuff built on top of Tekton. It's really become fundamental and core. It's a push-based model. There's another CI/CD system out there that's also open source, also part of the cloud native computing ecosystem. And it's called ArgoCD. And ArgoCD is a little bit different. What happens in ArgoCD is you put all that configuration in one GitHub, your YAML files and your Docker in one GitHub, you put your code in a separate one. And what Argo is smart enough to do is you point it at that repository, and it sees what you put in there, and it goes, oh, that's what you want? I'm going to pull that information, and I'm going to do that for you. So in Tekton, it's push, 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 build, build, build. You're controlling everything, and you got to have the right commands. Argo is going to go find your stuff, and if you change it, it'll realize you changed it in the GitHub repository. It'll pull the changes and deploy that way. And what's neat is if somebody goes in and hacks, because some of you look, I don't trust some of you. Some of you don't trust. You're going to go behind my back. You're going to go change that production environment. ArgoCD is going to realize you did that. It's going to say, no, the source of record's in the GitHub repo, and so I don't know which one of you changed it, but I'm changing it back. So ArgoCD is a pretty cool system. Okay, so we're doing kind of okay on time. I think I got like 20 minutes. That's the basics, right? That's the basics. We covered containers, Kubernetes, CI/CD. Now we're going to get a little bit advanced. We're going to cover what are called operators. So you've got Kubernetes, you've fallen in love with it, your pager doesn't go off in the middle of the night anymore, right? So life is good, but now you need to extend it. You need to extend it with a custom resource. You got something that you need a custom resource. And so if you want to add a custom resource to Kubernetes, the way we do it is with what's called an operator. It's the extensibility model for Kubernetes. It supports the same control loop architecture. I didn't cover it that much, but there's always a control loop architecture that's running that says, okay, what's your current state? What's the state you want to be at? Let me try and get you a little bit closer to that state. Does that make sense? And so the reason they call it an operator is that it's a piece of code that typically has embedded in it the actual knowledge of what an operator would do, your systems administrator operator would do. It's going to do automated software configuration and the stuff typically done by a human operator. And it's going to typically handle the more complex lifecycle management, version upgrades, failure recovery, scaling. And the nice thing about operators is seamless integration in Kubernetes. It's real hard to tell the difference between a basic Kubernetes resource and an operator custom resource. So the big question you should be asking is, wait a minute, you told me how great Kubernetes was, and now you're telling me you need this thing called operators. Why do you need these operators, right? And we can see over on the right, this was the classic Kubernetes example I talked about. A pod crashed, Kubernetes recognized it, and it starts up a new one probably somewhere else on a different node. So the deep dark secret is Kubernetes is great for what are called stateless applications. Stateless applications, like a web application server typically stateless. But what about stateful applications? Stateful applications are things like databases, things like things that need leader election, things that need backup and recovery, things that need lifecycle management. So the operator gives us the ability to extend Kubernetes, but for those custom resources, it gives us the ability to add in those needed extra steps. And so if we need to do leader election, or if we need to do something else because it's a stateful-based application, that's how we do it. The operators are really powerful. If you look at Red Hat OpenShift, everything's done with operators, from the basic provisioning to sizing up the cluster, so initiating the cluster and managing the cluster size, managing the cluster version, configuring DNS, all of that's done with operators. I listed on the right here a ton of operators that you can see. And so how do we use an operator? Again, I mentioned it was seamless. It was seamless, right? So if we look at, I've got a custom operator here for memcached, right? So memcached, a very popular application, has a lot of state. And what you're seeing over here on the right is a new YAML. It's got a new kind called memcached. It's got a name, and it's got a custom field, size 3. So we've got this, it looks just like all the rest of Kubernetes if you look at it, but it's got a new kind value. So again, the operator is still using the declarative model. We're going to be able to create that resource using a YAML and be able to do a kube control apply. So if you're a person using this custom resource, it feels just like the rest of the Kubernetes. It feels like a deployment. It feels like the other stuff I showed you. And then you're going to write what's called a controller loop, and the controller loop is going to do all the fancy stuff to make sure that what you want to happen, lifecycle management-wise, actually happens. There's a great operator SDK is another open source project that allows you to build operators. It supports Helm operators, Ansible operators. Go is the most popular, and Java. So there's a link here. If you really want to go build an operator, that's the right way to do it. Very powerful. It's going to generate, that operator framework is going to generate it's called the operator SDK, is going to generate most of the code that you need. So it's going to generate your custom resource definitions. That's what describes what are the fields in your custom resource to Kubernetes. It's going to generate that skeleton controller. That's that loop that's always running. It's always obsessive. What's my current state? What's my desired state? What do I need to do to get a little closer to my desired state? And then it just keeps going and going and going. So that's going to give you a skeleton version of that. And then, the most difficult part of an operator is building that custom reconciliation loop. And this is sort of a tour talk, not my deep operator talk, so we're not going to go into too much detail on that. You're probably happy about that. It gets a little interesting. But all right, so going back to that memcached example, The memcached operator, it's got two basic fields. It's got a size, the number of copies of memcached that are actually running, and then it's got an output field and status, which is the number of nodes, the names of the nodes where the application is running. And if you go look at the implementation, this is like the hello world operator. It actually reuses the deployment resource underneath, so it reuses that as well. And so you can see the two fields in purple there, size equals 3 and the nodes, and that's what it would look like. There's some values here that I've colorized. So there's the API version. We're going to call it cache.example.com, and v1 alpha is the version. And so there's actual operator SDK commands down here. I'm not going to go into too much detail, but that's how you define those values for your new operator. So example.com, we're calling that the domain, and that's where it maps in the thing. If we look at the group is the cache, the version's v1 alpha, and so the create API command, that's what tells it what those values are. So those are operator SDK commands that do that for you. And then there's some other commands that'll generate the skeleton code for those fields. And again, we talked about two fields. One was size, and so it's an int32. And the other one was that name of the nodes where things are running. And the operator SDK gives you a make generate command to generate the code, and then we run a make manifest, will generate the CRD manifest. So you get the code, and then you rerun it, and then what is happening is you're describing the new fields that you need, and all of this is describing how it's going to be able to explain to Kubernetes how to store your fields in Kubernetes in its key value database called etcd. So a lot of magic is happening, but it's writing most of the code for you. The hard part is what's called writing a reconciler loop, and again, just runs in a loop. And there's a couple ways it can return, right? So it can return, if it's made progress and it's gotten to the desired state, it does a return with a requeue, which means, okay, there's more work to be done, so go back into the loop again. The next one is, well, there's more work to be done, but I just started something. It might take like 10 seconds or a minute to start. So there's the return and requeue with delay. Hey, if something went wrong, there's the return and requeue with an error. And so you'll say, hey, try again, but there was an error. And then if you finally get everything done right and you get to your desired state, there's the return and exit. So those are typically the different types of things. I'm not going to go into all the code on this one because it gets a little complicated. But again, it's how do you write one of these? Sequence of small iterative steps. Fetch the existing state, determine what action you need to get closer to your desired state, and then take an action to get closer and then return, and that loop just keeps running. This stuff comes from an old, way back when, I think control theory was a way we used to do these loops. So they're reusing some old technology like we always do in computer science. Here's some pseudocode for that memcached reconciler. I'll go real fast because I want to get to the other topics. But hey, we fetched the memcached resource. Oh, if it doesn't exist, it was deleted. If it's deleted, I don't have anything to do. It's gone. If it does exist, let's see if it's got a deployment resource underneath. If it doesn't, let me create that, and then I'll requeue and then go back in the loop. If the deployment resource exists, let me find it, make sure it's got the correct number of replicas. If it doesn't, I set the size to be the right set. If the deployment has the correct number of replicas, I update the status, and if we finally get to where everything's the way we want, we exit. So I covered that a little quicker than I would have liked, but we got to keep moving. This is just showing you that you run this memcached with that kube control apply command and pass in a YAML, just like the rest of Kubernetes. So no different there. All right, so we're going to get to the last topic here. I got 10 minutes. I think I'm doing OK. Cloud native applications. These are complex. They run across multiple nodes. They're distributed applications. Big questions we typically encounter. Why are my problems happening? What performance bottlenecks, failure points, unexpected behavior. At what stage did the failure occur? Where's the bug occurring? So a lot of work is done in what we call observation techniques, metrics collection, distributed tracing, right? We want to understand what's happening in our cloud native application that typically runs across multiple nodes. And so what's the challenge here? A lot of languages. Everybody's got their favorite language. Everybody, you know, how many people here write in Go? All right? How many people write in, you know, PHP? Anybody write PHP, right? So here we are, everybody's writing in their own language, and somehow we've got to find a way for everybody writing in their own language to be able to instrument things and have all that trace work and that metric work, no matter what language and application they're writing in. And then, oh, by the way, if that wasn't fun enough, you started with one visualization tool. Maybe you started with Jaeger or Prometheus or Instana, but then maybe you want to move to another. So what would be the worst situation in the world? That you pick a proprietary tracing model and now you're stuck. You're stuck with the one tool, and it was good last year, right? But the people got lazy, and this year the tool stinks, you want to move. And you can't, right? Because you were locked in. So that's the challenge of observability. So how do we address that? Open Telemetry, another cloud-native open source project, right? This is OS 101, and every project I've mentioned, none of them are proprietary. They're all open source, right? And so what does it do? It's an open source observability framework. It gives you distributed tracing, metrics, log collection, and it supports client instrumentation. They've got a whole bunch of people working on the instrumentation for you, so whichever language you have up here, whether it's Ruby, Swift, Go, .NET, whatever, everyone, Python, whatever you want, they've got people out there working on the instrumentation for your beloved language that you like because you just didn't want to change. And you take the Open Telemetry and it gets things to an intermediate format, and that allows you to pick whichever visualization profiling tool that you want. That's the power of Open Telemetry. So again, it's open source, it's a standardized approach. It supports multiple programming languages. It's got all your favorite features, tracing, metrics, log data. And it's allowing you to support multiple back-end data formats. There's no vendor lock-in. It's as easy to send that same instrument data, you start with one and you realize you don't like it, you can move to a different vendor's tool. And you're basically doing instrumentation in a standard vendor-agnostic way. That's where the whole industry is lined up on this Open Telemetry stuff, and they're all cool with the Open Telemetry protocols for sending things, and then you can very easily create what's called an exporter and use any back-end visualization tool you want. And so when we think Open Telemetry collector, what are the main components? You're going to see these things called receivers. Those are things that receive the data. They might receive metrics data, they might receive how many processes are running, and they might be receiving the trace. But they receive the data that's going to then go into the collector. And then when it goes into the collector, we have what are called processors. One of which is called a batch processor that's going to place things into batches. One's a memory limiter that'll keep, if you got a whole bunch of trace coming in, it's going to prevent out-of-memory situations, might drop data, might do garbage collection. So you got receivers, you got processors, and then the fun part that all the vendors work on, at IBM we have Instana, but we have exporters. So you got that intermediate common format, but then when it's time, you can then export it to any tool you want. And there's Jaeger, Zipkin, Prometheus are all popular choices. Again, we talked about three types here. There's traces, or usually what's used a lot. They are made up of units of work called spans. There's metrics, there's logs. I'm going to show you a manual instrumentation, but most of these cool frameworks like .NET and Python have built-in instrumentation. So a lot of this you don't have to write yourself, but I am going to show you writing it yourself just so you can learn a little bit. Simplified tracing example. Very simple routine here. We're calling a routine called Fibonacci. And so, write ends up calling Fibonacci. And so I've created some distributed tracing, and the units of work are called spans. And so I've got two spans here. And what's really neat is, you've got the Fibonacci span in the trace at the top, and it's telling you, but I've got a parent. There's more to me than meets the eye. I've got a parent, and if you check, that span ID for the parent matches the span ID for the write method. So this is how you can do distributed tracing and understand what values related, what calls were related, nested in other calls. And then there's also other routines I didn't have time to show here where you can store all kinds of interesting state data in your tracing. So what this gives you is the ability to do what we call distributed tracing. And what's hard about tracing is when you're trying to trace through a whole application that crosses multiple nodes, that's where all these span values and trace ID values show you that path across the distributed environment. That's when that becomes really valuable. Doing great on time. We got 3 minutes left. If I time this right, there's no time for questions. If you want to learn more about all this stuff, we offer free courses. You can order you get a badge if you take the course, and so if you want to take a snapshot, you can. A lot of free courses on Kubernetes, containers, OpenShift. Operator learning path at IBM, an IBM developer. We've got a whole thing about all, I know I went really fast here and it was like way too fast, but all the stuff that I talked about in wonderful detail is in that operator's learning path. You can go learn that. Feel free to take a picture if you want. So quick summary at 312, again, cloud native technologies, they got key features for building scalable cloud-based applications. We talked about containers and packing everything up and being really efficient, more efficient than virtual machines. Kubernetes gives you that orchestration and provisioning and restarting stuff when they fail. The operators allow you to add custom resources and allow you to worry about stateful applications and lifecycle management. And then Open Telemetry was, for observability, your distributed tracing, your metrics, log collection, no vendor lock-in. So numerically, I did cover this in time. If I was betting, I didn't think I was going to get near half this, but we did. I do have a recent book that I published that covers a lot of this in more detail. There's a link if you want to go buy it. They actually make them still in paper too, so do that. And that's all I have.